Swayam Prabha. Digital India. Educated India.
Welcome back, everybody. We did talk about chemical shifts. We did talk about spin-spin coupling in our previous video. We're going to touch on integration. We did talk about chemical shifts and spin-spin coupling in our previous videos. We are going to talk about integration today. So this is the topic of the day, and we're going to do integration using examples. So after the machine has plotted your peaks at the very end, if you had one of those old plotters, you'd see it go and draw a line parallel to each of these peaks. Nowadays, it will just tell you the heights of that and give you how many protons are underneath each peak. So it'll take the area underneath each peak and give you a ratio here. The area underneath each peak corresponds to the number of protons in that particular environment at that chemical shift or delta. So we can find out how many protons are in here that have this environment and that are unique, and how many protons are in this particular environment, and they are also very unique. Typically these would be on a particular carbon and these would be on another carbon, but not necessarily. Let's look at the three different things that are important. First, chemical shift. Chemical shift is how much it has shifted from TMS, which is the standard, and we give it as a ratio of the shift over the machine frequency. In this case, this is going to be 1.6 ppm. So this is a ppm scale. I'm not sure if you can see it, but this is a ppm scale for the chemical shift of that proton. This is 1.6 for A. So we only have two peaks. So that's one of the important pieces of information. Number of peaks tells you the number of different protons in different environments. Okay, types of protons. So here we only have two types, A and B, two types. For the A, the chemical shift is 1.6 ppm. For B, the chemical shift is about 3.4 ppm. Now, the other very important piece of information is spin-spin coupling. How many peaks do you have for each of those peaks? How many splittings do you have in each of those? So A has got 3, so that's a triplet. B has got 4, that's a quartet. This is what we mean by integration. We take the ratio of these heights. Most of the recent NMRs would give you the number, but here in this case they haven't. And if you have one of these, this is how you do it. You have to have a ruler. A centimeter ruler would be best, or millimeter, and you are going to see the heights of these. The height corresponds to the area, and that corresponds to the number of protons of that type. So number 2 is the chemical shift. Chemical shift talks about the electron environment. So the chemical shift talks about the electron environment. Here's just a diagram to show you what the chemical shift can do in the presence of electrons around a proton. Here is a proton. Here's an electron cloud here surrounding the proton, which means it's in a sigma bond here. The sigma bond is nothing but a pair of electrons or electron density that is around the proton. The external magnetic field. It is going to hit that proton. If you didn't have an electron field, electrons are nothing but negatively charged particles that are spinning, so they have their own diamagnetic field that opposes the external magnetic field. If you don't have an electron cloud, it's going to hit that proton and you're going to feel a very big applied magnetic field. So therefore the energy level here between these two spins would be a lot larger. Therefore, the frequency would be larger. So as BO increases, frequency increases, and we saw that over and over again. So if you don't have electrons around it, you'll have a higher frequency, which means you are going to shift away from TMS and have a larger delta. And so here, that is going to be called downfield. So this is very important. So over here, hydrogens, shielded environments will have a lower B and a lower frequency. So they are going to be shifted towards TMS, upfield. That means towards TMS. If you have hydrogens that are de-shielded, then they are going to have, just like we mentioned before, there's no electron cloud, you're going to get hit by the BO and your frequency will be higher. When you have more and more electrons surrounding it, then the applied magnetic field is opposed by the induced magnetic field of the electrons, so your BO is lower and your frequency is lower and your chemical shift is lower. So therefore you're going to go downfield, which means you're going away from TMS. So those are the two things that we can tell from here. In this compound here, which one do you think is going to be shielded? Which one do you think is going to be de-shielded? De-shielded means your electrons are pulled out by an electron withdrawing group. So you have a CH bond, but you have neighbors that are very electron withdrawing, so it thins out this electron cloud. And that's pretty obvious here. You're close to the bromine, so these protons are going to be very de-shielded. This hydrogen is on a carbon that is next to another carbon. Therefore, these are more shielded. So this will have a higher frequency of resonance, and this would have a lower frequency of resonance. De-shielded, shielded. Upfield, downfield. The third one is the multiplicity. Okay, so multiplicity tells you who's your neighbor, how many neighbors do you have. Triplet means you have 2 neighbors. Quartet means you have 3 neighbors. So this proton has 3 neighbors, and these protons have 2 neighbors. For these protons, you have 2 neighboring protons. So n plus 1 would say 2 plus 1, 3. So you get a triplet for this. And that's exactly what you see. So here, this should have a higher delta, which means these are your B protons at 3.4. This should have a lower chemical shift, that's A. This is going to have 3 plus 1 quartet. And this is going to have 2 plus 1 triplet. The next most important part is the integration that we're talking about here. So again, multiplicity is equal to, given by the equation, n plus 1 is multiplicity. N is number of neighboring protons. We're coming to then the next most important part, which is what we're going to talk about today, integration. Integration is telling you the ratio between these 2 protons. So let's measure it out, shall we? So always when you have an NMR exam, make sure you take a ruler, a centimeter ruler, so you can do integration. Let's take our ruler, measure it out. A is going to be 4.5 centimeters. And B is going to be 3 centimeters. 3.0, let's say. And we know that this is in a ratio 2 to 3. And if you divide both of these by 1.5, you can see it's giving you a ratio 3 to 2. So this again, HA, and I will label this HA, and this is HB. HA has got 3 protons, HB has 2 protons. So it tells you not only how many different types of protons you have, but also the ratio of hydrogens in those different types of protons. That's very valuable information. So here we have CH3, CH2, and you can see that reflected in the number of hydrogens. Okay. The last one, and this is really probably the most important of all, is neighboring protons. Okay, this is important to solve for an exact structure. So here, if you have a triplet, then if you have n plus 1 is equal to multiplicity, which is a triplet, and triplet means you have 3 splittings. Therefore, you can solve for the neighboring hydrogens, which is going to be 3 minus 1, which is 2. So you can see over here, A over here has 2 neighbors. It's not the number of protons on the carbon. That's not N. N is neighbor. That's something to remember. Okay. N is neighboring hydrogen. So if you take A has 2 neighbors, and you can see that is correct. If you take B here, it's a quartet. So N plus 1, we don't know what N is, but we know the formula for that is 4. Quartet is 4 splittings on that line, on that peak. Therefore, N is going to be 3. So B would have 3 neighbors. And that's what we see. So all of the pieces of information that we have looked at so far all fall into place here. Okay, and I'll write that down. Number 4 is going to be integration. And that tells you the number of protons, of hydrogens, of each type of proton, each type. And the type is given by the number of peaks. All right, so that really kind of brings home some of the things that we talked about. Let's do an example problem here. Let's look at this one. They're telling us this is a spectrum of an ester. An ester has 2 alkyl groups that are flanking a carboxylate group, which is a C double bond OO group. So this is going to help us then decipher the exact structure of or structures of these R's. And they may be different, they may be the same. We don't know. We just have to solve for it. Okay, it's a puzzle. So each NMR is just nothing but a little puzzle. It's like a jigsaw that you just put together the pieces, and then the picture pops out at you, or the molecule pops out at you in this case. All right. So here we know that that's the functional group. We have over here 4 carbons, and we know that one of the carbons would be for the carbonyl. And so we have to know then what's on the left and what's on the right of this carbonyl. So we'll have 3 carbons that would go into the side chains of the alkyl groups. There's also chlorine over here. Let's look at it, shall we? Let's do the same thing we did. So always have like a plan for each one. And well, this is my plan. I usually make a table, put all the data in, and then try to make connections inside to see what's coupled to what. That's how I usually go about. So let's label this A, B, C, and those are the 3 peaks. So peaks are 3, A, B, and C. Let's look at the shifts, chemical shift delta in ppm from TMS, which is set to 0 by the machine. So this is shifted here to 1.3 for A. This is delta ppm. And for B, it is 4.1 about. And for C, it is 4.4 about. That tells us the number of peaks and the types of protons. So we have 3 different proton types. That's what the spectra is telling us. Let's look at, well, the multiplicity is the most, like the obvious thing here. Let's look at the multiplicity here. And let's say this is going to be a triplet. B is just 1 line here. That's a singlet. And C has got 4 lines here. That's a quartet. So that's the multiplicity. The next one is the integration. Let's look at the heights here and see the ratio here. These will tell us the number of protons of each type, or the ratio. They can be a empirical ratio, and you may have to multiply them by a number, let's say 2 or 3 or whatever. But in this case, if it matches the one in the formula, then the empirical formula and the molecular formula ratio is the same. Okay, so here is, let's say the integration tells us the number of hydrogens. So this is where you use the integration. A to B to C ratio. A to B to C. That's what we call integration. And that would require a ruler. Okay, so you would take a ruler and go out and measure the distance here. So we have a triplet, and that is about 6 centimeters for A. We have a 4 centimeter and about a 4 centimeter. They're both equal here. So you could say that, well, if you divide everything by 2, you could get a 3 to 2 to 2. And that adds up to be 7, and we have 7 protons. So we don't need to multiply this or do any other operation to it. It's the same. This is the empirical ratio, and it's also the molecular ratio of hydrogens. So so A to B to C hydrogen ratio by centimeters is 6 centimeters to 4 centimeters to 4 centimeters. If you add this up, it would be 14, but we only have 7, which means we have to divide everything by 2 because we only have half the number of protons, which is going to give you a 3 to 2 to 2 ratio. So we know how many protons are buried underneath each of these peaks. How many protons of A type and B type and C type are here on the spectra. So this gives us a very nice proton ratio or hydrogen ratio, which is really very important to proceed. The next most important or valuable information is going to be then the neighboring protons. And we know n plus 1 is m, and so we can use that to find the number of neighboring hydrogens. Not the hydrogens on the carbon, but the one on the neighbor. Okay, that's something to remember, especially at the beginning, because most people think this n means how many hydrogens are on that particular carbon. No, it's on the neighboring carbons, and you can have 2 neighboring carbons, and it could be a total of both of them. So here, m is triplet, that means 3. So n plus 1 is 3, therefore n is 2. So A has 2 neighbors. Let's talk about B then. B is a singlet. That means you have n plus 1 being 1. Therefore, n is going to be 0. B has no neighbors. C here has got a quartet. That means n plus 1 is 4, and therefore n is 3. So C has 3 neighbors. Let's try to make some connections here. So A has 3 hydrogens of the same type. Maybe they're all on the same carbon, like a CH3, and that has 2 neighbors. This has no neighbors, so therefore this cannot be next to this or next to this. Let's look at this. This has got 2 hydrogens and has 3 neighbors. So does that ring a bell here? 3 hydrogens, 2 neighbors. 2 hydrogens, 3 neighbors. Who do you think they're next to? That's right, they're next to each other. They're neighbors. And we can then talk about this structure when you have a triplet quartet, that you have both of these next to each other. So you have 2 hydrogens that are next to 3 hydrogens. So if you take this hydrogen, the CH2, which is the C here, and the CH3 triplet, which is the A here, this is a quartet, this is a triplet. Whenever you have a triplet quartet, which we saw here, it is always an ethyl, because n plus 1 here for this is going to be 3 neighbors. 3 plus 1, which is 4, which is a quartet. So for A, you have 2 neighbors. N is equal to 2 here. over here, so n is equal to 2. So 2 plus 1 is 3, which is a triplet, and that's what we see. Here, n is going to be equal to 3. All right? So it fits perfectly. So we know we have an ethyl here. All right, so we have some pieces of information. The problem here tells us it's an ester. So we know that we have a COO group, carboxylate. This piece of information tells us we have a ethyl group somewhere. It could be on this side or on this side. We don't really know. Now, B here is something we got to address. B doesn't have neighbors, so it cannot be here or here or here. Methyl groups are caps. You can't go past them because you'll violate the octet rule. So therefore, we are just for right now going to put CH2 here. And we also have, in addition to that, a chlorine. And where can the chlorine go? Well, there aren't too many places. We cannot put it anywhere here. Oxygen, chlorine, well, what about here? So that's a likely possibility. So NMR doesn't really leave us with too much room for choices because it tells us exactly the order in which these are arranged. So the ethyl, let's look at the chemical shift to see if the ethyl should be connected directly to the oxygen or directly to the carbonyl. We saw earlier in the chart, and you can refer to that, if you're connected directly to an oxygen, that's very de-shielding, and it's going to be between 3 and 4 for these hydrogens. If it's connected to the carbonyl, carbon, it's going to be between 2 and 2.5. So let's check the chemical shift for this carbon here. That's going to tell us. So this carbon is going to be the one that is C over here. This is your C. And so that is 4.4. So obviously it's not attached here. It's directly attached to this. So that's the information that the chemical shift tells us. Delta 4.4 means it's very de-shielded, means it's next to an oxygen and not a carbon. Now this is going to be 1.3, and that makes sense because this is not directly connected to the oxygen. It is a primary and it is connected to a carbon. Okay, so therefore, yeah, this is not as de-shielded as this. Now, where would you put this? We don't have too many choices because NMR kind of really puts all the pieces in a certain order. So if you take this, is it possible to put the chlorine here? And CH2, obviously not. Chlorine is monovalent. And let's look at the chemical shift of this. So this is going to be our C, and this is going to be our A proton, which means this is our B proton. And the B has no neighboring hydrogens. It is 4.1. So over here, this is also very de-shielded, which means it's next to an electron withdrawing group, and well, carbonyl too. So here is a carbonyl, and here's an electron withdrawing group, and that can put it together. Now, does the multiplicity make sense for this? This has no neighbors, therefore it's going to be a singlet. This has 3 neighbors, 3 plus 1 quartet. This has 2 neighbors, 2 plus 1 triplet. So yes, that makes sense according to this. The delta values make sense, the multiplicity makes sense, and let's look at the integration and see if that makes any sense. So A has 3 hydrogens, B has 2 hydrogens, and C has 2 hydrogens. 3 to 2 to 2, which is what you see on the chart and on the NMR integration. All of these pieces then come together to give you a beautiful structure for your NMR spectra. So this is something that we are going to do more of in the days to come. We will just do more sample problems to show you how to solve for a structure given an NMR spectra. Okay, we are kind of done talking about theory. Let's get down to business. Solve all of those NMR problems that are in your book. One of the best ways to do NMR is to do them. Just practice. Okay, so if I put up a spectra, please don't wait for me to work it out for you. Take out your notepad, work it out, and then just look at it. I mean, we're not grading you on what you're doing at home, so you can make 100 mistakes and it's fine, but please try them out. Talk to you soon, and we will see you with more problem solving. Good luck, guys, and I'll see you soon. Bye.